Welcome to Easy Elim Learning Simplified. My name is Ruth, and today we are going to be looking at the topic structure of the atom and periodic table, which is Form 2 topic. We are going to look at the subtopic isotopes for today. Previously, we talked about how to show electronic configuration and also drawing electronic configuration structures, the dot and cross structures. So you can check that out in the previous videos. So for today, we look at isotopes, and then we also calculate the relative atomic masses. And finally, we'll do a few questions or practice. So first of all, isotopes are atoms of the same element with the same atomic number, but different mass number. Another way of seeing it is that atoms of the same element with the same number of protons but different number of neutrons. So if you look at the examples given, an example of an isotope is hydrogen. You can see hydrogen exists in three ways. So this is how they are existing into the Earth's surface. So we have the hydrogen, the tritium, and tritium. You can see the mass numbers are different because of the number of neutrons. And we have chlorine 35 and chlorine 37. The reason why they are different is because of the number of neutrons, but you can see the number of protons are the same in both cases. Another example is potassium 39, potassium 40, and potassium 41. You can see they have different number of neutrons. And another example is oxygen. We have the 16 and 18, and you see one has 8 neutrons, the other one has 10 neutrons. We have uranium 235 and uranium 238. It has 143 neutrons, the other one 146. But you can see the number of protons are the same in both cases. And finally, we have neon. Neon 22, neon 20, and neon 21. So they have different number of neutrons. So when you're defining, you need to remember they are the atoms of the same element. So this brings us into relative atomic mass. So when it comes to the masses of different atoms, calculating the masses of each atom sometimes can be very negligible and not that easy to weigh. So we cannot just weigh each and every atom every time we want to get a specific mass of that atom. It is so small into that value. 10 times power negative 20. It has a very big decimal value, which is very negligible. So for this reason, so atoms are usually expressed relative to a chosen standard element. So the one that was used before was hydrogen, which was later replaced by oxygen. So oxygen was not found that useful, so later on it was replaced by carbon 12. So when we define the relative atomic mass, we're always defining it in relation to carbon 12. So relative atomic mass, it's the average mass of an atom compared to a 12th of the atom of carbon 12. So that is the definition of relative atomic masses. When we are calculating its relative atomic mass, that is the average mass of that one atom of that specific element you want over the 12th mass of the carbon atom. So the accurate values of relative atomic masses are also gotten from mass spectrometer. This is a topic you learn in mass spectrometry, that is in campus, those who are going to do chemistry. And we shall talk about isotopes in the instrument that is used to measure, and it is in comparison to how much they are available on the Earth's surface. So when you are using relative atomic masses, we're usually using a specific value that is gotten from the mass spectrometer. And relative atomic mass is usually calculated using this method. Normally, we have the relative atomic mass is equals to the mass of the isotope times the relative abundance times over 100. So if you have more than one isotope, you just add a positive sign and repeat the same formula. We're going to do examples on the same so that you can be able to see the different ways the questions can come in this subtopic. So let's start with one question. A neutral atom of silicon contains 14 electrons, 92% of silicon 28, 5% of silicon 29, and 3% of silicon 30. That means on the Earth's surface, 92% of silicon 28 is one that is most abundant in the Earth. And then silicon 29 is abundant but not as much as silicon 28. And finally, we have silicon 30. So that's the reason why we usually use this formula. It's not easy for us when you compare these three atoms of the same element to know which mass number to use for our calculation. So we do an average, and that is what we refer to as the relative atomic mass. So let's calculate the relative atomic mass of this silicon isotope. So we said that the relative atomic mass is equals to the mass of the isotope. So the mass of the isotope, you're going to take one by one. So let me write the formula again. And then times the relative abundance. It's usually in percent form, but the question can come in different forms. And if we have another one, in this case, we can add another one depending on the number you have. And everything is divided by 100. So let's do that together. So our RAM in this question will be, so we start with the 92%. Silicon 28 has a mass of 28. We put a bracket, then we add a plus sign. The second isotope is 5%, and the mass number is 29, and the third is 3%, and the mass is 30. So everything is going to be divided by 100. So let's put the values. So this first value gives us 25, 76. And then this second value gives us 145. And then this value gives us 90. So we're going to add everything and divide by 100. So 2,576 plus 145 plus 90 will give us 2,811. If you divide this by 100, it will give us 28.11. So this is the relative atomic mass, and you can see it's close to the value that is most abundant, which is the silicon 28. You can see the mass is 28, so it is closer. So that's how you can confirm if your values are correct or not. Let's look at another example. So element X consists of two isotopes whose mass number are 35 and 37. They exist in the ratio is 3:1 respectively. Determine the relative atomic mass of X. So ratio 3 represents the one with mass number 35. Ratio 37 represents the one with mass number 37. So the first step that we are going to do is we are going to get the total ratio. So the total ratio is 3 plus 1, which gives us 4. So the x35 will have a fraction of 3/4, while the X37 will have a fraction of 1/4. If we look at the total abundances for both isotopes, it's supposed to total to 100%. So we can be able to get the percentage abundance for each isotope. So isotope 35, we are going to take 3/4, we multiply by 100, and then isotope 37, we are going to take 1/4 and multiply it by 100 as well. So by 4, and then we get 25. So 25 times 3 will give us 75%. And then by 4, 1, by 4, 25, which will give us 25%. So the percentage abundance for isotope 35 of X is 75%, and isotope X37 is 25%. Next, we go to the formula, which is RAM is equals to, we pick the percentage abundance, which is 75%, times the mass, which is 35, and then we add 25%, times 37, which is the mass, everything over 100. So when we calculate 75 times 35, we get 2,625, plus if we multiply 25 times 37, we get 925. Everything is done over 100. So we are going to add 2,625 plus 925. We are going to get 3,550 over 100. If we do this division, it means we get 35.5 hours as our relative atomic mass, which is closer to the one that has the highest abundance, which is X35. Let's do another example. So another element, P has two isotopes with relative abundances of 65% and 35%. If the mass number of the two isotopes is X and 31, so we have P X and we have P35, and Px is 65% because we have been told respectively, and P31 has 35%. So using that information, our relative atomic mass is equals to, so we pick the percentage abundance 65 times the mass, which is X, and then we put a bracket, we add 35% times the mass, which is 31, and then we divide everything by 100. And the relative atomic mass we have been given, we have been told from the question, find the mass number of X given that the relative atomic mass is 30. So the answer to the relative atomic mass here is 30. So we change our equation to become 30 is equals to 65 times X plus 35 times 31 over 100. So that becomes 30 is equals to 65 times X becomes 65X, plus when you multiply 35 times 31, you get 1085, everything over 100. So first we need to remove this denominator. We do so by multiplying everywhere by 100. So we multiply this side by 100. We multiply this side by 100. So this 100 cancels with this, and we have 100 times 30, which gives us 3000, which is equals to our 65X plus 1085. So we put like terms together by bringing the 1085 this side. So it was positive sign. When it moves to the other side of the equal sign, it changes to a negative. So it becomes 3000 minus 1085 is equals to 65x. So if you subtract 1085 from 3000, you get 1942, which is equals to 65x. So if we simplify this expression to be left with only x on one side, we'll divide both sides by 65 and we get the value of x as 1942. If you divide by 65, you're going to get 29.876, which if you round off to the whole number gives you 30. So the relative atomic mass is 30. You can see why, because the mass of isotope X or P30 Px will be 30, not the relative atomic mass. The mass of X will be that. So we have P30 and P31. So those are our answers. So let's look at one more example. So lithium has two isotopes, mass number 6 and mass number 7. If the relative atomic mass of lithium is 6.94, determine the percentage abundance of each isotope. So we have lithium 6 and we have lithium 7, and our relative atomic mass is 6.94. So the first thing that we need to realize is if you take the percentage abundances of each isotope and add, you're going to get that the total abundance for both lithium 6 and lithium 7 is going to be 100%. So if you are going to take an assumption that lithium 6 has a percentage abundance of X%, then it would mean lithium 7 is going to have a percentage abundance of 100 minus X. So that is what we have been doing all along. So the only difference is that we are giving it a known value. So let's put that in the equation. So the relative atomic mass is 6.94, which is equals to percentage abundance of lithium, which is X%, times the mass, which is 6, plus the percentage abundance of lithium 7, which is 100 minus X, times the mass, which is 7. Everything is going to be divided by 100. So if we multiply both sides by 100 to remove the denominator, we get that 6.94 will multiply by 100, which will give us 694. If we open this bracket, 6 times x will give us 6x, plus, if we open this inner bracket first, we are going to get 7 times 100, which will give us 700, and then 7 times x, which will give us 7x. And remember, it's minus because the minus still remains. If we multiply this positive value with minus, it becomes minus. So that is what we have. So let's open this equation. So it becomes 6x plus 700. So plus minus, it becomes minus. So we put like terms together. So we can decide to take them in both sides. So we can take the 7x here to become 7x and also the 6x this side. So it becomes minus 6x. We can see why. We had minus 7x. When it comes this side, it becomes positive, which we do not have to write. And then 6x, when it comes this side, it becomes minus. So the equal sign and then 700 and then the 694 comes this side and it becomes also minus. So 7x minus 6x gives us 1x, which we write x, and then 700 minus 700 minus 694 gives us 6. So the value of X is going to be 6%. So lithium 6 will have a percentage abundance of 6%, while lithium 7 will have percentage abundance of 100 minus 6, which gives us 94%. So those are our answers. Let's do one last question and then we close. So element X has atomic number 16 and has two isotopes. So we have 2 over 3 of isotope X33 and a third of isotope 30. So we can either check the fractions and get the specific abundances. So 2 over 3 times 100% and 1 over 3 times 100%. So if we take 2 over 3 times 100%, we get 66.67 into decimal places. And if we take a third multiplied by 100, we get 33.33% into 2 decimal places. So those are the percentage abundances. So you use that. Relative atomic mass is equals to 66.67% times the mass, which is 33, plus 33.33 times the mass, which is 30, everything over 100. So when you calculate 66.67 times 33, we get 2,200.11. And when we take 33.33 and multiply it with 30, we get 999.9. Everything is divided by 100. So next we need to add the 2,200.11 plus 999.9 together. We get 3,200.01. This is divided by 100, which gives us 32.0001. In whole number, it's 32. So this is close to, you can see it's in between, close to percentage abundance that is highest. So that's how you work it out. So if you notice, when you come to 67, when you look at this expression here, so 66.7 times 33, if you divide this by 100, it's the same as 2 over 3 times 33. The same case, if you take 33.33 times 30 divided by 100, is the same as 1 over 3 times 30. So you do not have to go to this long method. You can choose to use the fractions as they are, and you still get your answer. So if you were to use the fraction, it would be 2 over 3 times 33 to bracket plus a third times 30, and you get your final answer. You don't have to divide by 100 because it has already been worked out. So that brings us to the end. I hope you have been able to see the different ways of calculating different ways of the question being tested, and you have been able to understand. See you in the next lesson.